Okay, starting section 2 now, we're going to be finding volumes using something called cylindrical shells. Now, I know that probably doesn't make sense at the moment, but it will here in a minute. So before we talk about what that means, let's look at an example where the disk method or the washer method just really wouldn't help us. So we're still finding those volumes using revolution, but the washer method is just not going to really work. So here's our example. The region enclosed by the x-axis and the parabola y equals 3x minus x squared is revolved about the vertical line x equals -1 to generate a solid. Find the volume of the solid. Okay, so in Desmos here, I graphed this. I have the parabola 3x minus x squared, and then the vertical line x equals -1. So here's the graph. So this red line here, that's the 3x minus x squared parabola. The blue line here, that's the axis of revolution, x equals -1. So what we're going to be doing is bounded by the x-axis here. So it's this shape here. And we're going to be taking this area and revolving it around the blue line. So it's going to make kind of like a donut looking shape when we revolve it around, like a flat bottomed donut. So if we were to try to do the washer method, right, we could not do the disk method because the area is not bordering the axis of rotation. If we tried to do the washer method, we would have a problem. The problem would be is that we're revolving it around a vertical line, so we're integrating along the y-axis, which means that your disks are going to have your washers, sorry, are going to have an outside radius and an inside radius. The outside radius goes to the edge of the parabola. The inside radius would go to the inside edge of the parabola. So you would be defining your outside and your inside radius using the same parabola on the same y-axis, and it just wouldn't define itself correctly. Now, it is possible to do it this way, but you would have to do two separate integrals, and it would just get really, really ugly. So we need to come up with another method of finding volumes using rotation or revolution like this. And the way to do that is going to be using something called cylindrical shells. So just kind of the gist of it is instead of making horizontal slices here, and then when you revolve those horizontal slices around, you end up with those washers, we're going to be making vertical slices. So we're going to make slices that are parallel to the axis of rotation. I was seeing if I could draw. I can't. I'll go over to my page here and I'll kind of recreate this and draw a little bit. So just moving over. So I already have an x and y axis here, but if I draw the parabola, just the area that we care about, and then I'm going to draw the axis of revolution, which is here at x equals -1. Okay, so if I'm revolving this region around that axis, again, I could not do horizontal slices because the in and the out of the slice would be defined using the same equation because it's the same parabola, which would cause issues. So instead, I'm going to be making these vertical slices. It's a horrible slice, sorry. And what we're going to do is we're going to take these vertical slices and revolve those around the axis of rotation. And if you revolve that around the axis of rotation, I'm hoping that you'll see you're going to end up with these cylinders. Kind of a really ugly picture, I know. So let's go over to the book, and the book has much better pictures than what I can draw on this thing. If I can find the book. Oh, here. Okay. So here's that same problem, just kind of graphed out. Here we have the 2D version where you have the area and the axis of rotation. Here you kind of have a 3D representation of what the solid would look like when you did revolve it around that axis of revolution. Okay, I know it's kind of hard to see in here because they have the 3D version and the cylinders on the inside. But basically what we have is that if you're going to make vertical slices of that area and then revolve that vertical slice around the axis of rotation, you're going to end up with these cylinders. What we're going to do is look at every single possible vertical slice, which is going to create every single cylinder, which will then kind of map out the total region. Okay, so there's a lot of math behind the scenes here, and I'm going to try to simplify that math down here in OneNote. The only thing I want to point out before we move over there is that when you do have a cylinder, to find the volume of an open cylinder like this, if you were to take that cylinder and stretch it out, it would end up being a rectangular prism. So the volume of a cylinder is really the same thing as the volume of a rectangular prism. Okay, so just kind of the math behind what we're doing here. So if we do have some kind of region, and we're going to take that region and we're going to separate it out using those vertical slices. So let's just say that this is my region going from A to B, and we're going to partition this like we always partition this into in different partitions. And let's say we're here at the moment at x sub k, and then the next one, maybe the one behind it, x sub k minus 1. Okay, so if I want to find the total volume of all of these slices, right? So maybe my axis of rotation is over here and we're revolving it around this way, where this is the slice I'm looking at the moment. If I want to find the total volume, I would need to find the volume of just one slice. So let's find the volume of this slice here that's located at K. The volume of this slice again comes from the rectangular prism after you like fold out the cylinder. So a rectangular prism is just length times width times height. So the length of the cylinder is going to be the total circumference of the cylinder, where the circumference of the cylinder is going to be 2 pi and then whatever the radius is. All right, so that's the length. And that's going to be times the width. So if we were to stretch this out, the width would actually be the vertical distance here. So the vertical distance, we'll just call it the height of your slice. That's going to be times what am I missing? Whatever it is. It's this little tiny distance that's the depth of the slice, but that we're just going to label as dx, right? Because remember that with these slices, they're supposed to be infinitesimally small. Okay, so the volume of just one slice is 2 pi, the radius of that slice, the height of that slice, and then the width of that slice, which is just going to be dx. Now that's just the volume of one slice, so what we're going to do is we're going to add up every possible cylinder, and then we're going to take the limit as n goes to infinity. And whenever you have a finite sum and you take the limit of that sum going to infinity, that creates the integral. So that leads us to our final thing here. With cylindrical shells, the total volume is going to be the integral from A to B of 2 pi. And there's not really a better way to write this except whatever the radius of your shell is going to be, the height of your shell times dx. So I'm going to go over to the book here because, of course, my handwriting is really awful and they have a little bit better way of writing that out. So the final result of all of this, well, they take a couple of pages to do what I did in about 3 lines here. So this is the shell method or the cylindrical method for finding the solid, the volume of the solid revolution. The volume is the integral from A to B, 2 pi, the shell of the radius of the shell times the height of the shell dx. These are both usually going to be functions of x, so we have to find those separately. So let's do one quick example in this video, and then I'll probably just be done with it after that, because it's the same concepts as like the disk and the washer method, where you could also do the cylindrical method with respect to y or x. So let's do this one and let's be done with it. So just quick example here. Make sure my thing's still recording. The region bounded by the curve y equals square root x, the x-axis and the line x equals 4 is revolved about the y-axis to generate a solid. All right, going back over to my notebook here, y equals square root x, the x-axis, and the line x equals 4. So just to kind of graph that out. Sorry, I had some leftovers from earlier. If you have our x and y axis, y equals square root x is this graph, the x-axis, and then the line x equals 4. So this is going to be my region here. And we're going to take this region and we're revolving that around the y-axis. So we're revolving it this way. Okay. This is a question where you could honestly do the washer method. Remember with the washer, let's just go ahead and do both, because why not, right? So let's do it using the washer method, and let's double check to see if we get the same answer when we come over to the shell method. With the washer method, remember the formula, V equals the integral of just pi, the outside radius squared minus the inside radius squared. But we have to be careful. Because the axis of rotation is vertical, that means that we're going to be having horizontal slices, which means that we're integrating with respect to y. So my outside radius is going to be a function of y squared, minus the inside radius is going to be a function of y squared, dy. And there should be parentheses around this. Okay, so I need to find my outside radius and my inside radius. Again, this is the axis of rotation. So my little slices here are horizontal. Remember that the outside radius is the furthest distance away from the axis of rotation. In my region, every single slice is going to have the furthest distance be at the vertical line here, x equals 4. So my outside radius is just going to be the distance 4. It's a constant the entire time. My inside radius, on the other hand, always comes to this square root x graph. But we have to be careful, right? Because right now we have it as y equals square root x, but we need it as a function of y. So that means we need to solve this for x by squaring both sides and rewrite this as x equals y squared. That is going to be the inside radius. All right, if I plug this into my formula now, it's going to be the integral. We do have to worry about the limits. We're going along the y-axis here. So my region starts at y equals 0, and it goes up to the y value at this intersection point here. But that y value would just be plugging 4 into the square root graph. So it's going to a y value of 2. All right, pi. The outside radius squared is just 4 squared 16 minus the inside radius, which is y squared all squared, y to the 4th. All right, we can pull the pi out and go ahead and do the antiderivative. 16 is just going to go to 16y. Remember, we're taking antiderivative with respect to y. Y to the 4th is going to go to 1/5 y to the 5th. And that we're going to evaluate from 0 to 2. So if I plug 2 into here, still have the pi on the outside. 16 times 2 is 32, minus 2 to the 5th is also 32 fifths. Minus, if I plug 0 into this, I just get 0. So just real quick, I didn't bring my calculator. Well, whatever that is, that's the answer. Let me pause it and I'll go get a calculator. Alright, so just plugging that into the calculator real quick, we get this. 128 pi over 5. Okay, so that was using the washer method. I'm going to jump to a new page here. And let's do the same thing, but let's use the shell or the cylindrical method instead. Just to recopy the picture over, we have our square root graph, x equals 4, and then the x-axis to create our region. We're still revolving that around the y-axis here. Okay, with the shell method, your slices are going to be parallel to the axis of rotation. So now these are my slices, and this slice is going to be located at x along the x-axis here. And there's a slice at every single x value going from 0 to 4. Okay, just to write the formula down for the shell method, the volume is 2 pi times whatever the radius is times whatever the height is. And then you have to worry about whether it's dx or dy. It's going to be dx, right? If you have vertical slices, those slices exist along the x-axis here, so we're integrating along the x-axis. What we need to do is we need to come up with the formula for the radius and the formula for the height with respect to x. This is going to become a cylinder, right? When I revolve it around the y-axis here, we create a cylinder. we need to figure out what the radius of that cylinder is and what the height of that cylinder is as we move along the x-axis, right? We're initially going to start with very, very skinny cylinders that are very, very small, and as I move up the x-axis here, they're eventually going to get very, very wide and very, very tall. Okay, radius first. The radius of the cylinder is going to be the distance from the axis of rotation to your slice. If your slice is located at x, then the radius is going to be a distance of x every single time. Well, not every time. For this question, every single time. It may differ depending on where the axis of rotation is. Okay, so the radius is just x because that is the distance from the slice to the axis of rotation. The height is going to be the vertical distance of your slice. If you have your slice located at x, then it is going from the x-axis or 0 up to the graph square root x. So our height, square root x. Okay, now we just plug those into the formula. So our volume is going to be the integral. Because we are integrating with respect to x, the slices exist from x equals 0 to this, which remember was at the vertical line x equals 4. So my limits go from 0 to 4 of 2 pi, the shell radius, which is x, the shell height, square root x, dx. Why can I not go down here? Oh, that's cool. I can make it the whole page. Well, that's nice. There, I'm going to cheat it so I can actually go down some. Okay, so just to do this integral real quick, it's not a hard one. I'm going to go ahead and take the 2 and the pi out of the integral. What I would do with this is that this is x to the 1, and here we have an x to the 1/2, and if we multiply those two things together and just add the exponents, we can think of it as x to the 3/2. Power rule here, we would raise that 3/2 up to 5/2 and then divide. So this is going to have antiderivative of 2/5 x to the 5/2, and then we're evaluating that between 0 and 4. Why can I not scroll down farther? Is there some secret to scrolling down in this thing? If you know, let me know. Okay. I did a little mistake here in my stuff, so I had to cut into the video. Whoops. Okay, here we go. Fixing my mistake, and you guys won't even know it happened. So we're going to pull the 2/5 out, and that'll be a 4/5 pi. Then, if I plug 4 into just the x to the 5/2, that's going to be 32. Minus, if I plug 0 into that, I get 0. All right, and then 32 times 4 is 128 pi over 5. And yay, right? Because remember, 128 pi over 5 was the same thing that we got when we did the washer method. So the shell method and the washer method do the same things. It's just that sometimes the shell method is easier to do, and it all has to do with defining your slices. If parallel slices are easier to define, do the shell method. If perpendicular slices to the axis of rotation are easier to define, do the washer method. But that's it for section 2. Got it done in one really long video.